Alrighty. Let's give this a second to kick in. Okay, let's see. Good morning. So let's see. We are going to continue our hybridization fun that we started last time. So I'll just give everyone a second to get in here. This is not going to be an easy class today. It'll be our last hard one, though, in my opinion, at least until the... Actually, it'll be the last hard one of the semester, again, in my opinion. So, again, this is like super conceptual stuff that can be tough. So, I'm going to give us our handy-dandy cheat sheet to hybridization. So we can actually base our hybridization based on electron geometry. If you have a tetrahedral electron geometry, you're going to have sp3 hybrid orbitals. You're going to have 4 sp3 hybrid orbitals. And if we were to draw them, we would see that they're going to kind of be in that shape if we were to draw them. So if you have 4 domains, you have 4 hybrid orbitals. It's not too bad. If you have 3 domains, you're going to have 3 hybrid orbitals. And a p orbital left over. So 3 hybrids for 3 domains. So guess what? Anytime you're kind of bonding to your domains, you're going to have hybrid orbitals. And guess what? How about this one? We're going to have 2 sp orbitals, 2 hybrid ones, and 2 p orbitals left over. Let me close the door real quick. Okay, there we go. So this is our cheat sheet. If you can identify the geometry, you can identify the hybrid orbitals that are participating within that bonding. And there's whenever you hybridize, if you're not using all of your orbitals, you'll have a few left over. So with these sp orbitals that we're going to have here, for example, we end up having 2 regular p orbitals that are not hybridized. So the ones that let me get rid of that underline. This 1p or the 2p orbitals are unhybridized. They are unhybridized p orbitals. And so we're going to see that hybrid orbitals contribute single for the sigma bonds. We're going to see that unhybridized they're going to make double or triple bonds. And those are called pi bonds. So let's take a moment here to look at a few molecules. Looking at formaldehyde here, what kind of geometry is this going to have? Or we're looking at the central atom, of course. Yeah, it's trigonal planar, right? Which means that we are going to be using sp2 orbitals for sigma bonds. And we're going to have 3 of them. So we're going to use 3 sigma orbitals. Which ones do we think those are going to be? Well, I guess that's going to be kind of hard for you to answer. I'm going to do them in blue. We're going to see that these single bonds and one of the bonds to oxygen are going to be in this navy color. Those are going to be the bonds made by our hybrid orbitals. And so remember that hybrid orbitals are going to make our single bonds. Anytime we have a double bond, we're going to have to add on some pi orbitals. So we're going to see that this one in green is going to be our pi orbital here. For the double bond. So we're still going to have 4 orbitals, just like we would always have. We have 3 of them that are hybridized, and we have 1 that is unhybridized. Looking at this, if we were to try and draw this molecularly, I don't know how this is going to turn out, but let's see. If we think about carbon as this little dot here, we have a hybrid orbital going to a hydrogen, another hybrid orbital going to a hydrogen. So here are our hydrogens. We have our oxygen here, which is going to be using hybrid orbitals also, but let's not worry about that. Ooh, that's really ugly. Oh god, that's even uglier. Okay, I can do this. Okay, so that's carbon in the middle there, and here's our oxygen. I'll just draw them like this. So this is all flat and planar. Did I just write H? Whoops. So we're going to see, in fact, that the p orbitals, remember p orbitals just look like dumbbells that are equivalent in size. Hybrid orbitals have, a small side and a big side. Actually, let me delete those, because when we bond them together, those p orbitals will in fact kind of bend towards each other. And they're going to be able to interact. Gosh, this is so hideous. Let me see if I can find a nice picture for you guys. Okay, let's see if I can find something really nice in our Google Images. Let's see. What did I use? Formaldehyde? Yes, I did. Cool. Yes, kind of. This is kind of what I'm going for. Oh, that's... Yeah. Keep looking at this hideous thing in the meantime while I find something nice for us. Yeah, that's kind of what I'm going for. Okay. Switching over. So, our green ones are going to be our hybrid orbitals. Those 3 are bonding with the H's and the oxygen, forming our single bonds. We have this kind of red p orbital that's going up and down. And so when these form the bonds, we make the sigma bonds between the carbons and the hydrogens using their hybrid orbitals. We make our single bond between the carbon and the oxygen. Since oxygen is also going to be sp2 hybridized, we have lone pairs in the other hybrid orbitals. And we have this pi bond, which is going to be on top and underneath, which is made using those p orbitals. They're going to kind of bend towards each other and fuse together and make this sort of pi thing. So, I mean, you can see all sorts of similar things happening here where we have this kind of overlap of the... Oh, here we go. This is exactly what I wanted. So the p orbitals overlap, not nearly as nicely as a sigma bond does. Sigma bond, you have actual physical overlap of the orbitals. However, this pi thing, they're kind of just stretched kind of together. They're not truly overlapping, but there's kind of this region that they kind of bridge between each other. And so we're going to see that one of those is going to be, that kind of sharing is going to be the pi orbital, the pi bond. And so because there's not a true overlap, let me go back here to our regular thingy. Do you like my beautiful drawing by comparison? Sigma bond has true overlap in your orbitals. Pi bonds are partial overlap. Or they're a kind of fake overlap. I don't want to say partial. It's kind of a bridge overlap. And so we're going to see that pi bonds are going to be weaker than sigma bonds. I know how beautiful that drawing is. But pi bonds are also going to be kind of special. Because if... Let me draw another one for us here. Whatever, here's some hydrogens around, just so we make our carbons happy. If we look at this one, and I just draw the pi orbitals, I'm going to forget about the sigma ones. Single bonds, who cares? What actually will happen here, interestingly enough, is we have these pi orbitals overlapping with each other a little bit. I'm drawing them kind of overlapping, but there we go. What's interesting is that we can also kind of form a bridge in between two adjacent pi bonds to each other. Let me see if I can have a nice picture for this. Let's see if we have a nice one. This is more not what I'm going for. But essentially what you can have is this what I'm looking for? Yeah. Yes, those are all from p orbitals. Yes, in this case 2p's, yeah. So this is kind of what I'm going for. So if we have two pi orbitals kind of just, oh, this is still ethene. Let me see if there's a good example of this. A nice blobbing of them. Aha! This is what I'm going for down here at the very bottom. Ignore all this other crap. What we can actually happen is all four of these can kind of overlap with each other, can form these bridges between each other. And so that's going to show that these electrons can actually travel basically the entire length of this system. And so we're going to see that this is basically going to say that p orbitals can overlap over distance. And I'm going to kind of overlap with a fake thing. Don't worry, I know this sounds totally weird. All we need to know is that this would be what's called delocalized. electrons. So because the electron, each of these orbitals would have one electron within them, right? Those 4 electrons can just zip around happily between them. So I think I'm getting ahead of myself. Here is our sp2 orbital. And we have our lone p orbital, right? This is one of those carbons. We have one electron in the p orbital. That electron is free to move and bond with any other p orbital nearby. And so if we kind of have this chain of similarly hybridized molecules, if they have leftover p orbitals, those electrons can delocalize, meaning they can move very far away from the carbon that they're originally, from. So we're going to see that this is more for organic chemistry, just showing you what this kind of means. And so if you can delocalize, meaning move it away, this is something that's particularly stable. And so you're going to learn a molecule called benzene, which looks like this. Which has p orbitals on all the carbons. My gosh, this is just getting so ugly. I'm so bad at drawing these. I'm so sorry. Orbitals are not my friends. There. All of these have one electron in them, and they're happy to kind of, zip around. And so because it's in a ring, the electrons can just flow like crazy going between it. This is also how you have resonance structures. So resonance, remember, that's like when you can move a double bond to a different place and get an identical structure. And so these two, I don't want to put a double bond there. That looks like a double bond. Oh my gosh, go away. These two would be the same structure. They're both illustrating that you have these kind of delocalized electrons by having similarly hybridized carbons near each other. I know this is probably way over your head. Don't worry. We're not going to see this again until OChem. By then, you'll have a much better understanding of these orbitals. Let's just take a look, though. We can see in nice images that are not drawn by me, we can have very nice kind of overlap. So we can see that all of these pi orbitals in the benzene are able to interact with each other. And so we're going to see that normally they look like this, but when they interact, they kind of blob up together, which makes benzene extremely stable. And if we look at where the electrons are, this is called an electron density map here, we see that it looks like there's a little ring in there. And we can see that these electrons are going to be delocalized. They're free to zip around throughout this entire molecule, making it incredibly stable. So you're going to see in organic chemistry, benzene does not react unless you beat the hell out of it. So it's already very happy doing this sort of zipping around sort of thing. So there we go. So we'll often end up drawing benzene like this, where we have those carbons there, and we just have this circle in the middle illustrating that the electrons are delocalized. So that is why this particular molecule is very, very stable. So, all right, now you can forget that until organic chemistry. So get that out of your head. Well, you don't have to. Actually, please don't. It's a good thing to know. So, are you guys sick of this sort of hybrid stuff? Benzene is a different molecule. Oh, I didn't write the name, did I? Benzene is actually a different one. Yeah. You will see in OChem 2, you will have a chapter on electrophilic aromatic substitution and nucleophilic aromatic substitution, which deals with all the crazy stuff benzene will do. in certain situations. So you will see it as a very important building block for a lot of compounds. And if you look at, let's say, some drugs, let's look at what's a nice drug? What do we like? How about doxorubicin, for example, is an anti-cancer drug. Notice we have a bunch of little benzenes in there. And you can see actually they put the little dots in there as well to illustrate that kind of delocalization of the electrons. So you're going to see that a lot of molecules have this benzene in it, and it renders it very, very stable because of those delocalized electrons. So without beating this dead horse, suffice it to say that delocalized electrons can be detected by the existence of resonance. So a molecule that has resonance forms is more stable. You're going to see the answer for every question in organic chemistry is resonance. 90% of the questions, maybe. You can just say resonance and you'll get it right. Resonance is a huge factor for molecule stability. And so we're going to see molecules that can resonate will have great stability. So for example, sulfate as an ion is very stable. It exists as a polyatomic ion because it can resonate. We can basically go ahead and plop some electrons down there and make the double bond here instead. That's resonance, right? When we move, we're making different double bonds. And so we're basically, because these electrons can flow around, they're not going to be able to react with other things. They're kind of flowing around within their own molecule, delocalized, and so they're going to become unreactive. And remember, unreactive means stable. So with the electrons moving around within a molecule, don't react easily. And we're going to see that these resonances are always as a result of these pi bonds, the p orbitals that are causing this sort of thing. Okay, so this is kind of the big picture here. Here it is, big, big, big important thing. Big, big, big important thing. Big, big, big important thing. So suffice it to say, delocalized is good. That's all. The whole point of that thing. Alrighty. Let's talk now about molecular orbitals. Which is an interesting topic, suffice it to say. I'm going to show you one. I'm going to show you why do we have H2 but not He2. So our Lewis structure for hydrogen would look like this. For helium, I'm not even sure what it would look like because it's not gonna work, and I'll show you why. So, if we think about hydrogen, we have two hydrogen atoms, yes, and they have electrons. They each have this electron configuration. They have 1s1. They have one electron in the 1s orbital. we're going to see that molecular orbitals are basically combinations of atomic orbitals. So we're going to see that we can combine orbitals in two ways. We can have a way where, so remember that electrons can behave as waves, right? Actually, before I go through this, let's go back to waves for just a second. If we put two waves together, remember, if we add these two guys, we just get a big wave, right? This is called constructive interference. I believe we did this a little bit earlier. If we put two waves together that are kind of the opposite of each other, they're out of phase with each other, we get nothing. And this is destructive interference. So with waves, we can add them up. And if they're kind of in sync with each other, we make constructive interference, which means the waves just get added together. You get an extra big wave, a happy big wave. If your waves are opposite of each other, if they're out of sync with each other, they cancel each other out. Just like vectors, right? If you're pulling in opposite directions, they cancel out with each other. And that's destructive. We're going to see that this is a good thing. Constructive interference is happy. Destructive interference is sad. Sad things are going to mean high energy. Happy things mean low energy. So, that being said, let's go back to this blob that I've drawn here. We're going to see that this one down here comes from constructive interference of these waves interacting with each other. Remember, electrons do have some wave-like properties. This one comes from destructive interference. Here is just basically energy as our axis. We're going to see that we can make our electrons happy by adding them together constructively. If we do that, we just put the electrons into this orbital. These were the hydrogens here. We're going to put them into a low energy orbital. We always try and do that, right? We want them to interact happily together. And this one is called a sigma orbital. Hooray! Technically, this is called sigma 1s because it is a sigma bond formed from 1s orbitals. This one up here is called a sigma star 1s. This is going to be destructive, which we call anti-bonding. This one we call bonding. I'm going to show you in just a sec what these look like orbital-wise so you can kind of see what they look like. And so we're going to see that we have these electrons from the hydrogens. One of them from each s orbital is going to move into this molecular orbital in this bonding area, forming that sigma bond. Since we do not have any more electrons, we're not going to put any in that sigma star. But let's have a look. Let's see what this looks like. So when we have constructive interference, we have these two happy things interacting together. When we have destructive interference, the waves cancel out, meaning that no electrons can exist there. So if we're thinking about where these electrons are going to be, if you were an electron, let's look at these two scenarios and think where you would rather be. Consider you have a positive bit in the center. That's your nucleus, right? If you were an electron and you could be anywhere in this particular thing, you'd probably want to be in this overlap region, because you get to feel the positive, happy effects of both nuclei. So this is what a bonding orbital will look like. Because we have these electrons get to feel both nuclei. So because their waves can add together, that's a happy thing. They can both experience both nuclei. And so this is a good win-win situation for everybody. And so we're going to see that because those electrons are attracted to both nuclei, they're going to just kind of sit in the middle. And that's how we see a covalent bond. They're together. However, if we have bad things happening, you know, who knows? Maybe the electrons are just kind of chilling in their own thing. They do not want to be in that middle area because their waves would cancel each other out. And so, since they cancel out, they can't exist there. Accept it. If they cancel out, they don't exist there. So an anti-bonding orbital, electrons are repelled by the what's called a nodal plane, where destructive interference occurs. Black magic indeed. So suffice it to say, with all this craziness happening, this is good. This is bad. So bonding good, anti-bonding bad. This is low energy. This is high energy. All right. It's more stable to have these electrons attracted to both nuclei. That's what you need to take away from this. So a bonding orbital, electrons are attracted to both of them because they interfere happily with each other, and so they can experience both nuclei. That's a good thing. However, when they cancel each other out, that's not a good thing. This is just a situation that would be high energy. Electrons will avoid this if possible. So if we think about helium, helium, of course, has 1s2, sorry. We're going to see it's going to make the same molecular orbitals. And so let's go ahead and put in our electrons. We're going to see that we're going to put 2 electrons in. We still have 2 more electrons, though. So those electrons have to go into the anti-bonding orbital. So let's think about what that means. We have 2 electrons that are lower energy, 2 electrons that are higher energy. We're going to see that this results in no bond formed. The hydrogen example, we see that we have electrons in a bonding orbital. This is going to result in a bond being formed that is shared between them. With this one, because we have electrons in anti-bonding orbitals, that's extremely unfavorable. We don't like that. So there's not going to be a bond forming between 2 heliums. Not going to work. Let's find a easy way to deal with this. We're going to see that we're going to have a thing called a bond order. If I could spell order properly. Which is going to be 1/2 times anti-bonding. we're going to be able to see that the bond order is half of the bonding electrons minus the anti-bonding electrons. So if we think about hydrogen, let's scroll back up to its little thing. I'll show you how to construct these in just a moment. We see that we have 2 electrons in a bonding orbital, and we have 0 electrons in a non-bonding orbital. So that's 1/2 times 2 minus 0, which is 1. For helium, we saw that we had 2 in bonding, 2 in anti-bonding. That equals 0. So if you have a bond order of 1, that's a single bond. If your bond order is 2, that's a double bond, etc. We could also have partial bonds. That's totally okay. That's due to resonance, but we'll deal with that later. That's why we're not going to see a bond between helium. Helium will not bond with other heliums diatomically. Let's look at some more. Let me talk about how to construct these. MO molecular orbital diagram. So we are going to, the number of molecular orbitals is the sum of the atomic orbitals. So notice we had 2 atomic orbitals for helium and hydrogen. We ended up with 2 molecular orbitals, right? We're going to see this in examples. And we want to fill the electrons from low energy to high energy. We're also going to see that anti-bonding, let's not worry about that right now. Let's take a look at another example. Let's take a look at lithium. Let's see if lithium would exist like this. So lithium has 1s, 2s. We're just going to be working with homonuclear ones right now, the same nucleus together. Here's our other lithium. We're going to see, we're going to make a sigma 1s, a sigma star 1s. I've really drawn this poorly. Let me draw these a little bit higher. Oh my gosh, go away. These take up a lot of space. Oh my gosh. You go down a little bit. Yeah. We have our 2s orbital, 2s orbital. Oops. So let's go ahead and, so notice we have 4 orbitals. You know, we have 2 orbitals from each atom. So 4 molecular orbitals total. This would be a sigma 2s, sigma star 2s. And again, energy is always going up. So if we want to start filling these, let's start from the lowest first. We have 6 total electrons, right? We have 3 electrons from each lithium. So there's 2. There's another 2. And there's the last ones. So notice our core electrons are going to cancel each other out. That's always going to be the case. This is why we don't see core electrons doing any chemistry, is because their molecular orbitals cancel each other out. They're always going to completely fill their bonding and anti-bonding orbitals, so we're never going to see them again. We're not even going to worry about core electrons anymore. However, this tells us that we would end up with a bond order of 1. So this tells us this could exist. We could see lithium bonded to lithium. And if we were to try and do the Lewis structure, we would see, oh yeah, this is going to make... We could see that this would make a Lewis structure. It'd be a very bizarre one, but there it is. We would be able to connect them. Poof, there we go. We have made, as Star Trek fans will know, dilithium. There we go. Exciting stuff. So this tells us this could exist. All right, so essentially we're just kind of going here. Does this exist? Does this not exist? If we do beryllium, we're going to see beryllium 2 would not exist. We would see that its anti-bonding would cancel out the bonding orbitals. Yes. So this is number of bonding minus the number of anti-bonding. So we see here we have bonding, I'll put in blue. We have 4 electrons in bonding orbitals. And we have 2 electrons in anti-bonding orbitals. I want to do 3 more examples just to help show a couple of things. Because these are pretty boring. Nobody cares about dilithium. However, we do know that we have other diatomic molecules that are of interest to us. Let's take a look at nitrogen. I'm not going to draw the core electrons anymore because those are always going to cancel each other out. So who cares? This is kind of... Do I want to draw it this way? Yes, exactly. Yeah, you would only work with valence electrons because it's just ugly otherwise. Let's see if there's going to be a nice picture of this online somewhere. I'm not really seeing that. Okay, fine. So let's go ahead and look at this. I've again drawn them too close together. Oh gosh. With p orbitals, we're going to get something interesting happening here. We're going to see that this is what we end up getting. We're going to see that we're going to get, this of course is the sigma 2s here. If we think about p orbitals, I'm sorry, I've gone ahead of myself again. I get too excited. P orbitals. Oh god, this is always the hardest one to draw. So these are your 3 p orbitals, right? Assuming we have X, Y, and Z in the mix here. It turns out that one of these can bond with other ones horizontally. For example, we could see that we could have p orbitals overlapping this way. If we put two px orbitals near each other, they're not going to form a sigma bond, are they? So remember, this is overlap directly. That's a sigma bond. If we put, so that's a pz and another pz. If we have ones that are oriented in the x direction, those would be able to bridge but not overlap. So this is a pi orbital. And we're going to see the same thing with the like ones that are, it's always hard to draw the one that's going into the thing, but we're going to see as well here, py is going to give us pi orbitals as well. So that being said, I'm sorry I forgot to briefly go over that. This is what you always get with pi orbitals. You're going to get a sigma bond that's going to be from two pz orbitals overlapping. You're going to get a pi bond, two of them, from either px or py. Again, those letters just illustrate whichever direction your orbital is kind of pointing. And just like before, you're going to have the anti-bonding equivalent of those. So all of ours are going to look like this when we set them up. So we're always going to have this exact same idea where we have, we're going to have our p orbitals split like this. Two of them will be stuck as pi orbitals. One of them will be stuck as a sigma orbital. Okay, again, as long as you can, start with this, we're going to see actually, since it's going to be the same thing for the other two we're going to look at, I'm going to just kind of copy it for now. Oh, no, I can't. Okay, well, I'll copy at least the top half. We'll remember that for later. Let's do nitrogen real quick, and we'll see what the heck is going on here. So nitrogen has this electron configuration, right? Boom. As before, the lower energy ones are going to be completely filled. Don't even have to think about them. So now let's look at the p ones. We're not even going to touch d and f orbitals. Don't even think about it. Or hybrids coming from those, so don't worry. Looking at this, excuse me, we have 6 electrons for our p orbitals. So let's put them in. 1, 2, 3, 4, 5, 6. We're going to do the same thing we did before. Fill them unpaired until we have to start pairing them off, and always from low energy to high energy. So looking at this, let's look at the bond order of nitrogen. The bond order, how many bonding electrons do we have in this? Oh, I forgot the star on this one. I forgot the dots as well. 3 bonding electrons. Well, let me start by... Okay, yeah, Shane's... Okay, you've got the bond order already. Yes, you guys are way ahead of me. Yeah, so we have 2, 4, 6, 8 bonding electrons. We have 2 anti-bonding electrons, which, as you guys have both said, is a bond order of 3. And that indicates a triple bond. And let's see if we do the Lewis structure. Lo and behold, yes, indeed, we get a triple bond in between them, as predicted by the molecular orbitals. Hooray! Yeah, you could. Again, because they cancel each other out, right? So yeah, you could just say 6/2. No problem. So yeah, you can always just look at the let me see, lowest occupied molecular orbital and the highest unoccupied molecular orbital. That's a whole different thing. Let's not worry about that. But yeah, you could just do that, Shane. Totally. So speaking of which, when we look at oxygen, let's look at O2 next. And I'm just going to go ahead and look at the, let's just look at the P part. Actually, no, let's, yeah, forget the S. S is going to look exactly the same. In fact, oh, I already drew on it. Okay, never mind. You know what, I'm going to do it anyway. Sorry, just to make sure. Okay. Oxygen has the electron configuration like this. So we're going to get these two are filled. Who cares? Now we're done with them. Now we can ignore them. Now let's look at this. We have 8 electrons, right? So let's go ahead and plop them in. Oh-ho. Interesting. If we calculate the bond order, it's going to be 2, 4, 6, 8. I'm going to just include the S ones. You do not have to. That is okay. Minus, I see 4 non-bonding or anti-bonding electrons, which is a bond order of 2, which tells us we should get this, which lo and behold we do get from our Lewis structure anyway. Awesome. Let's notice something interesting about this. What do we see that's interesting about these electrons in the molecular orbital that we have not seen so far in any of the other MO diagrams that we've done? What's interesting here? Something we haven't seen before. Partial P's. Yes, I like that. You're noticing we have something that is special here, which are we have unpaired electrons. And we're going to see that if a molecular orbital has unpaired electrons, we get what is called paramagnetism. Which means that these are attracted to magnetic fields. The opposite is, I'll tell you, if there are no unpaired electrons, it's called diamagnetism. Diamagnetism, which is repelled by magnetic field. So interestingly enough, if you were to pour liquid oxygen, liquid O2, in between some magnets, you're going to see that the oxygen is actually going to stick to the magnets, which is pretty interesting to see. Whereas something like nitrogen, which we saw had no unpaired electrons in its molecular orbital, is diamagnetic and is going to be repelled by a magnetic field. So there are some interesting things here. So oxygen is paramagnetic. It can be attracted to a magnetic field. Sorry, let me scroll up a little bit. Let's see if we have any lovely images of that. Oxygen, paramagnetic. Let's see, do we have any evidence? Let's see. Aha! Oh, this is a YouTube video. Well, whatever. Let's go ahead and take a look. So someone's got this liquid oxygen here. Very dangerous thing to have. Liquid oxygen is pretty reactive, so at least this guy's wearing goggles. Okay, he's got his magnets here. I don't know what this is. Perhaps a transferring vessel. Who cares? What is he doing? Oh, this is liquid nitrogen. So he's actually cooling down the oxygen. He's making liquid oxygen over here. Forget it. There it is. Lovely. It's blue, did you know? Liquid oxygen is actually blue. Another fun fact for your friends. Very, very dangerous stuff. But here we go. He's just cooling down the magnet so that it doesn't have any problems. Notice that the nitrogen he's pouring is repelled. It's being pushed away by those magnets. And let's go ahead and watch him pour the oxygen now. And lo and behold, the oxygen gets stuck in between the magnets because it's actually attracted to them. So there's our evidence here. So if you wanted to just see again before, the nitrogen he's pouring does not do this. And in fact, you see it kind of splashing away like really easily. There's nothing in there. You see it's completely empty. Because the nitrogen is diamagnetic, it is repelled by the magnetic field. But the oxygen that he poured through got stuck in between because it is attracted to the magnetic field. So there we go. That's our fun fact for the day. Hooray. We're going to do one more example, and that's fluorine. I just want to show one more thing. We're going to do more of this, because I know this is not an easy topic. So on Monday, we will continue doing this. Okay, if we look at fluorine, here's fluorine. Bond order is going to just be 1, right? Interesting. Oh, by the way, on our Discord, remember I posted a happy, better chart than last time. So let's see. Discord, I think, is this one. I hope. Nope. Maybe this one. Yeah. I posted a real chart. By the way, the reason we got the enthalpy for propane burning was so low, we had a much different number for C double bond O. This one is the correct number. So this one is one we'll use. I wanted us to take a look at nitrogen, which has got a bond enthalpy of 941, which is versus fluorine, which has a bond enthalpy of 155. Why do we think fluorine has a much lower one? So fluorine is 155, but nitrogen delta H is 941. Why do we think it takes so much more energy to break the nitrogen apart than it does to break the fluorine apart? Taking a look at their molecular orbital. True, but that doesn't matter here because it's bonding with other fluorines. Yeah, so Kevin's got the kind of idea I was going for, and Shane, that's exactly the last point I wanted to illustrate. Yes, we have two anti-bonding here. Just looking at the P part, by the way. So we're going to see that this one is going to be much stronger. We have three very good things going for this nitrogen. For fluorine, we have three very good things as well, but we also have two very bad things. So as a result, it's going to take a lot more energy to break nitrogen apart because it has no antibonding orbitals filled in its kind of uppermost energy level there. Yikes. By the way, like if you just like Google these, you're gonna get prettier pictures than I'm able to illustrate here. For example, this is oxygen here. Notice how pretty this one is. You can see things very clearly and happily here. You know, so you can always kind of double check your answers here. Oops. And so you can see fluorine, it's got exactly the same thing that we've done, just more neat and tidy. Everything in period 15 will be stronger. Yes. I would say so. Though these become less apparent the higher energy we go anyway, just the difference between them is not as big. So, but here we go, we see fluorine, you can see the nice orbitals they've drawn here. So we've got our atomic orbitals on the left and the right, and we've got our molecular orbitals in the middle. Exactly. So theoretically, yes, that's correct for that logic. So when you're doing these, you can always kind of Google how you're seeing them, and so yeah, it's exciting. So I know this is a bizarre topic. This is, I think, is the last like hard lecture before the end of the semester. So, or at least the like hardest to understand. The rest is going to be pretty just algebra, easy math, going forward. Actually, maybe we'll have some crystal structure issues. We'll see when we get there. We get into geometry, but let's see what happens when we get there. So on Monday we will continue doing this. Natasha has reminded me I forgot to put up your homework yesterday for Lewis structures and stuff. I'll put that up. I'm actually going to put up both homeworks for this chapter for 8 and 9. That's the Lewis structures as well as the shape and all that fun stuff. And I'm going to make them due in 2 weeks. So it'll be next Sunday that they're due. So you're welcome to, of course, get started. I would recommend it for sure. Don't wait till the last minute. But the homework will be there so you can start looking at it. We'll just kind of touch on this again at the start of Monday. Just maybe do a couple more practice problems or something so you can see how these are done. But yeah. Cool. So tomorrow, if you guys wanted to do an exam review, throw your questions up in Discord as always. And I guess I'll see you here at 10:15. Alrighty. Have fun. I'll put up your homework. And yeah, we'll be good. Alrighty. Take care, everyone.